Hi everyone. So this is our last unit, Unit 6, and this is Lesson 1, Similar Triangles. Alright, so our learning goals for today, we are going to, by the end of this lesson, you should be able to show if two triangles are similar or not using AASSS or SAS. So that stands for angle, angle, side, 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 or side, angle, side. So we're going to look at 3 different techniques for showing that two triangles are similar, or if they're not similar. Once you figure out if two triangles are similar, then you can then use the fact that they are similar to find the side lengths on the missing triangles. So in other words, what I mean is, say you have two triangles that are similar, you know the side lengths on one triangle, and you know some of the side lengths on the other triangle. You can use the fact that they're similar to find the rest of the side lengths on the other triangle. And we use something called scale factor to do that. Similarly, if you know two triangles are similar, and you know something about the sides of one triangle, and you know something about the sides of another triangle, but not enough to get the area, you can use the sides from the original triangle and the area of the original triangle to find the area of a new triangle. We also use scale factor for this, but we use the square of the scale factor, and we'll talk about what that means later on. Okay, so similar triangles. What does it mean to say that two triangles are similar? So like these two triangles, they're similar. So they share the same proportions, right? You can see that all 3 angles are the same. So when triangles are similar, all 3 angles are the same, and they have the same proportions. So proportions have to do with something called scale factor, which we'll talk about in a second. So scale factor is just talking about, say, if you can think about zooming in or zooming out on a camera, or blowing something up so it looks bigger. That typically uses scale factor. So if you zoom in on a picture, it doesn't typically stretch a person's face or squish a person's face or something like that. Their face keeps the same proportions, and that's what happens when you have similar triangles. So these triangles both have the same proportions. So in other words, if you take this side, for example, this side that has a length of 3, and you double it, so you blow it up by a factor of 2, then it will have a side length of 6. But if you blow up this side by 2, to keep the triangle similar, you have to blow up every side by 2. So 4 will be blown up by 2 to give you 8. And if you know anything about Pythagorean theorem, right, 3, 4, 5 triangles, this side would be 5. So you can maybe guess this side would be 10, right? Everything gets blown up by 2. So 2 is the scale factor. And you might be familiar with this concept from geography class. It's the same idea, right? If you have a scale on a map. So I took this picture from Google Maps of Toronto Islands. So distance here is 500 meters in the real world. On my computer, when I did this, it was about 2 centimeters. So you are blowing up 2 centimeters massively to represent the real world here. So I just quickly did the calculations. So you want to be careful in this situation. This is just something good to know. If 500 meters in the real world is represented by 2 centimeters on a map, to make the comparison fair, you need to use the same units. So what I would say is that 2 centimeters on a map represents 50,000 centimeters in the real world, right? I convert 500 meters to centimeters. So if you remember, there are 100 centimeters in a meter. So we multiply 100, so we get 50,000, right? So if I have 2 centimeters on the map equals 50 centimeters in the real world, to get the scale factor, we just divide. So 50,000 divided by 2 is 25,000. And so what that means is the 2 centimeter version on my map, if I blow it up by 25,000, that would give me the proportions of the real world. But they would be the same, right? The distances on this map would be the same proportions as they would be in the real world. So this distance here is 25,000 times whatever I measure that as. And this distance here would be the same, and so on. Okay, so one of the main keys here is that when you have scale factors, you can figure out missing sides by using ratios if you know that the triangles are similar. So if I know these two triangles are similar, but say I didn't know this side was 8, if I know that the scale factor here is 2, because 6 divided by 3 is 2, then I could get this missing side, right? I could do 4 times 2 is 8, because everything must be in proportion if triangles are similar. Okay, so how do we know then if a triangle is similar? Because we can't do this kind of math unless we know for sure if a triangle is similar or not. So when we talked about the learning goals, we mentioned that there are 3 techniques you can use to prove a triangle is similar. You can prove that 2 of their angles are the same. So say this angle, and this angle, this angle. We said that in similar triangles, all 3 angles have to be the same, but you only need to prove that 2 of them are the same. Because if you prove 2 are the same, the third one must be the same, right? Remember that all angles in a triangle must add up to 180 degrees. So let's just say this one here is 60, and this one here is 90, and this one is 60, and this one is 90. Well, in both triangles, you've now used up 150 out of that 180 degrees. And so the remaining angle in both cases will have to be 30 degrees. So you only have to show that 2 angles are the same in both triangles. The other way you could do it is show that all the sides are related by a scale factor, right? So in other words, we know the scale factor here, if these triangles were similar, is 2, because 6 divided by 3 is 2. So if I knew all 3 sides, I could just check and see, is the scale factor 2 for all of them? If I do this side divided by this side, do I get 2? If I do this side divided by that side, do I get 2? If I do this side divided by that side, do I get 2? If I get the same number for all of those divisions, then I can conclude that the triangles are similar. Finally, I could do a combination sort of these methods if I can show that 2 sides have this scale factor property. So for example, 6 divided by 3 is 2, 8 divided by 4 is 2. If I can show that this angle between those 2 sides and this angle between the corresponding sides on the other triangle, if I can show that those 2 angles are the same and those 2 sides scale up in the same way, that also proves that the triangles are similar. Okay? So we know how to do sides and scale factors. I just kind of mentioned that, right? If you have some of the sides, you just figure out which side pairs with which, and you divide the sides and see what number you come up with. So that's how you test the sides. But what about the angles? I said you can check to see if the angles are the same, but how do you know if 2 angles are the same or not, right? Unless the question tells you, how do you know that? Well, you might have seen this stuff maybe in grade 8 or some other point in your math career, but here are some ways you could tell if angles are the same. So we have opposite angle theorem. If you have an X shape, then the angles on the opposite side of the X are the same. So this A and this A would be the same, these 2 angles. This B and this B would be the same. But note that A and B are not the same. So it only works across the X. It doesn't work beside. Although you can say something about the angles beside here. You can say that those angles add up to 180 degrees. Because if you have a straight line that's broken up, right? Remember, the angle of a straight line is 180 degrees. You can see that on your protractor, right? It goes from 0 to 180. So a straight line has an angle of 180 degrees. We call that a straight angle. And so if you divide that up into 2 angles, both of those must combine to give you 180. And we say that those angles are supplementary, if you remember that word. We already talked about this one. All angles in a triangle add up to 180. So if you know 2 of them, you know the third one. And we also have this useful property called parallel lines theorem. And there are a few different versions of it. So alternate angles is sometimes called Z pattern because you can sometimes draw it as a Z. So this only works if these 2 lines are parallel. And those lines we can see are parallel because there are the lines indicating the property of being parallel there. So if those 2 lines are parallel, then the angle here and the angle there are going to be the same. This looks like a Z, but it could also be if you go here, here, and there, you get a pattern that's kind of zigzaggy like a Z, but doesn't really look like a Z. It's maybe like a backward Z, or some weird transform Z. But in any case, this angle here and this angle there are also the same. So they alternate, right? If you go from one parallel line up to the other by crossing some other line, the alternating angles are identical. In addition, we have the F pattern, where this angle and this angle are identical. Again, lines need to be parallel. In addition to that, we also have the angle on the top here and the angle in the middle there. Those 2 angles are identical as well. So you can have like an upside down F and use the same property. If you combine this property with the supplementary thing I was talking about here, the fact that angles in a straight line have to add 1 to 180, you can understand where this comes from. So if this angle here in blue plus this angle here have to add up to 180, and they do because we have a straight line with this line separating them, so these two angles have to add up to 180. Well, if this blue dot and this blue dot are the same, and this have to add up to 180, then this and that also have to add up to 180. So in other words, these two angles here must add up to 180 degrees. So if you know this one is just 180 minus whatever the number is here. Okay, so that's all the ways that we can know angles in a triangle. There may be a couple of others, but that's what we're going to worry about right now. So just keep in mind that if you want to use any of these three methods at the bottom, your lines must be parallel. All right, let's get on to a couple of examples. Example 1, prove that triangle PSQ is similar to triangle RST. Okay, so this symbol means similar, and you can go PQS, so that's the small triangle on the top, and RST, so that's the larger triangle, basically the top part and the bottom part combined. So we want to prove they're similar, and remember that there are three ways we can do that. We can use two angles, we can use three sides, or we can use two sides and an angle. In this case, we only have two sides for both triangles, but the angle S here is actually shared between them. So we're going to use the two sides and an angle case. So we can say that angle RST, right, this angle S here, in other words, and angle PSQ, same angle there, they're the same because they're shared, right? The same angle is shared between both triangles. So I've already proven the S part of SAS, RST and PSQ are shared. So now if I can show that the sides are proportional, then I can say, yes, this triangle is similar. So side PS is just this little part here, that's 4. And side RS is the whole thing. So it's not just 12, it's 12 plus 4. It's the whole line. So 12 plus 4 is 16. And this is 4. So if we look at the ratio, we do the larger one divided by the small one. So 16 divided by 4, and that gives us 4. I want to see if I get the same proportion on the other side. So the small side here is 5. The larger side is 15 plus 5. So I have 15 plus 5, which is 20, divided by 5. And it turns out, yep, that also gives you 4. So these sides of the small triangle and the large triangle are proportional. They go up by the same factor, and the angle is shared. So by SAS, we can conclude that these two triangles are similar. All right, let's look at example B. We have triangle CBA and triangle FGH. I want to prove that these two are similar. Now, you want to be careful here, because in this case, the triangles do not have the same orientation. This triangle here is flipped a little bit. So you could tell that because if you look at the triangle on the left, side AC is your longest side, right? You have 84, 72, 48. This is your longest side. In this triangle, HG is not your longest side. It's HF that is your longest side. So we know that HF actually matches up with AC, right? So if you want to think about this, imagine this is like a book or something. If you flip this as if you're turning the page, HF should actually line up with AC. And that's important because you're dividing numbers on both triangles to try to figure out what the scale factor is. And if you don't recognize this, you might divide the wrong pairs of numbers and not get the answer that you're looking for. Okay, so we have three sides for each triangle, so we're going to use the side, side, side case. We have CB, which goes along with FG. So CB is 48, FG is 8. We get the ratio there, and that's 6. So if you blow side FG up by a factor of 6, you get side CB. Let's see if that applies to the other sides. So we have side BA. Remember that goes with GH, right? BA and GH are corresponding sides. So 72 divided by 12 is actually 6. So that's looking good so far. And then AC, which is 84, divided by HF, which is 14. 84 divided by 14 is 6. So we have a consistent factor. If you blow up any side on this triangle by 6, you get a side on this triangle. So 6 is your scale factor, and these triangles are similar by SSS. Okay? Now let's get into some word problems. So in this case here, in example 2, taken from your textbook, what you have are two triangles, and you have one side on this triangle and two sides on this triangle. Okay, so you have a willow tree, a maple tree, and a sumac bush here that have been represented by W, M, and S in this case, if you're wondering what W, M, and S are here. We also have A and B in this question. So we want to try to find this, the distance between the maple and the willow. That's what the question's asking us to find. So how do we do that given the information that we have? Well, you can see here that you only have one side of this triangle. So we could maybe use the Pythagorean theorem, right, because this is a right angle triangle, but we only have one side, so we can't do that. So we're going to have to figure something else out. We do have two sides on this triangle, though. So if we can show that these triangles are similar, then we might be able to get another side on here, and we might be able to solve the problem. So we can't just assume these two triangles are similar because they look similar. You have to prove it first, and then you can do it, because we're not told these triangles are similar in the question. So how do we show that these two are similar? There's a few ways to do it. So I'll cover the way it's done here, but I'm going to give you one other way that you could kind of do this, or one other part that you could have included here if you wanted to. So what they've done is they've used opposite angles theorem to show that this angle here, ABS, and this angle here, MBW, these two angles are actually the same by opposite angle theorem, right? By that X pattern. The opposite sides of the X will be the same. So I already have one angle being the same between the two triangles. The other thing that they do is they use parallel lines theorem, a Z pattern, which doesn't look much like a Z. But you can see that this line here and this line are parallel. The question tells you that. That's what these arrows mean. So they show you that you have this, and that. So this angle here and this one there are alternate angles. Again, it doesn't really look like a Z because this is a 90-degree angle, so it doesn't bend backwards. But you can still use this idea. So this angle here is the same as that angle there by parallel lines theorem, the Z pattern. So you've proven that two angles of these triangles correspond to each other. They're the same angles. And therefore, that's enough to show that, yes, these two triangles are similar. The other thing you could have done, if you wanted to, is because these two lines are parallel, you have a Z pattern there as well, from this way. So this angle here and this angle there also match. So you could have used that instead if you preferred. But anyways, you've now proven that these two triangles are similar, and that means their sides are proportional. So side BM and side BS go together. They're proportional. Side AB will go with this hypotenuse here, because they're both the hypotenuse of the triangle. And that means that this side is proportional to that side. So if we could get the scale factor, we can figure out how much we need to blow this up by to get that. That's all you got to do. So we just need to set up a ratio. Okay, so let's see that. So BM over BS will give you the scale factor. So from here to here will give you from there to there, right? And it's a little bit tricky maybe to see which sides correspond, but I think you can see if you rotate this one this way, right? So if you rotate it so that this piece goes there 180 degrees essentially, you're going to get, well, you'll have the triangle in the same orientation that this is. Your hypotenuse will line up. That's kind of key, right? You can kind of see that you have to rotate this all the way around for this hypotenuse to match up with that one and for your right angle to match up there. Okay, so that means that BM and BS are proportional. So let's figure out what the scale factor is between them. So 24 divided by 9.3, which is what we're doing here. So 24 divided by 9.3, it says here that they're going to leave the scale factor in this form for more accuracy in later calculations. So you could, in other words, get 24 divided by 9.3, get a decimal number on your calculator, but that's going to round. So you could just leave this like that and then figure things out after. So we're just going to leave it as 24 over 9.3. If you did it as a decimal, not really a big deal. Okay, so we know that this is the scale factor, 24 over 9.3. So that's your fraction there. So what's the scale factor? How does that play into the other side? Well, if this goes over that, then this will go over that, right? These sides correspond. So this divided by this gives you the scale factor. So this divided by this should give you the same scale factor. It should give you 24 over 9.3. So WM divided by 8.4 will give you the scale factor. And now you can calculate it, right? Because all you got to do is this number, whatever this works out to, multiply both sides by 8.4 to get rid of the 8.4, and you isolate for WM, which turns out to be about 21.667. So that's the length across the river. Okay? So the other thing that they mention in here, this has to do, if you cover this in science, sometimes you might have heard something called significant figures, but basically you can't necessarily always add extra decimal places after this because we're not actually able to measure them. Our measuring devices are not perfect, right? Like imagine trying to measure 21.667 centimeters on your ruler. There's no way you're going to get that small. It's going to be inaccurate, so they cut that part out. Don't worry about that. I'm not going to ask you to do that. I'm going to tell you if you need to round your answer, how much you can round it by. Okay, example 3. We're going to try and figure out our third learning goal here. What is the relationship between area between similar figures? And you have similar rectangles here because it turns out it doesn't matter what shape you're talking about. The same idea applies. So it applies to triangles, it applies to rectangles, and any other shape. Okay, so we can find the areas of the figures. Remember that the area of a triangle is half of base times height, so you just sub in some numbers because they give you those. They tell you these are similar, but again, you can check if you wanted to, right? See, they have a scale factor of 2 here. So it turns out if you calculate the area for the first one, you get 6. If you calculate the area for the second one, you get 4. So what is the connection between 24 and 6? Well, 6 is 4 times smaller, right? So 6 times 4 is 24. So what they're trying to get you to kind of see here is that your scale factor, we said, between these two is 2, right? 10 divided by 5 is 2. 8 divided by 4 is 2. 6 divided by 3 is 2. So the scale factor between the triangles is 2. But the scale factor between the areas is 4. And so as it turns out, and we'll be able to show this in a minute, the area doesn't scale up the same way that your sides do. Your area scales up by scale factor times scale factor, or scale factor squared. And that kind of maybe seems like it would fit because if you have, say, a distance of 3 meters, if we're talking about length, we're talking about area, you wouldn't say 3 meters. You would say 3 meters squared. So area involves squaring things. So when you use a scale factor and you're trying to use that to compute areas, you're not using the scale factor, you're using the scale factor squared. You can see that's also true of the rectangle. So scale factor here is 4, 8 divided by 2 is 4, 12 divided by 3 is 4. So yeah, these are similar rectangles. They all have the same angles and proportions. Note that for a rectangle, they're always 90 degrees here. So saying that 3 angles, sorry, I guess 4 or 2 or however many you want, right? Saying the angles are the same in a rectangle doesn't prove that they're similar because the angles in a rectangle are always the same. They're 90 degrees. So you have to go with the proportionality of the sides to see if rectangles are similar. But in any case, those two are similar, and you can see the same pattern applies. We said the scale factor is 4. So the area, though, doesn't go up by 4. It goes up by 4 squared. So 6 times 16 is 96. So if the sides scale up by 4, the areas scale up by 16. Okay, so part B, we just computed the scale factors. So I already mentioned that. And then, yeah, so I've covered all this stuff in what we just said, right? So this is telling you that it's squared rather than just scaling up. And here we've calculated what the scale factors are. Okay, so this always applies. So let's try and understand why that is, because it's pretty easy to understand why. So let's look at the rectangle, because that's a nice and simple example. So the rectangle A, the small one, its length is 3 and its width is 2. And for rectangle B, its length is 12 and its width is 8, which means the scale factor is 4, as we just said, right? 3 times 4 is 12, 2 times 4 is 8. So let's look at the area for the larger rectangle. So that's going to be 12 times 8. So remember that this is the side of your first rectangle blown up by a factor of 4, and this is the side of the first rectangle blown up by a factor of 4 as well, right? So we start with 3, we blow that up by 4 and we get 12. We start with 2, we blow that up by 4 and we get 12. So let's show that, right? 12 is 3 times 4. And then 8 is 2 times 4. You have the original sides here, and you're blowing them up by 4. So that's really what you've got going on here, right? 3 times 4 times 2 times 4. So it's multiplication. We can rearrange stuff however we want, right? 3 times 4 is the same as 4 times 3. So we'll just rearrange it so the 4s are in the front. And so now you'll notice here I have 3 times 2. Well, that's the area of your original figure, right? The area of your original figure is 3 times 2. So on the outside, I have 4 twice because I had to take 4 out of both sides. And so that's why it's 4 squared. You have 4 twice. 4 times 4 is 4 squared. Okay? So you don't need to prove that, but you might need to use this idea that when you're scaling up areas, don't go by the scale factor, go by the scale factor squared. Okay, so I believe we are into our last problem now. Example 4. The shaded area is to be an industrial zone. So zoning of areas in a city, right? So you might notice that in certain areas they have industrial buildings, in certain areas they have commercial buildings. Maybe you've covered this in a geography class of some kind, but you're allowed to build certain buildings in certain places and not allowed to build them in others. So this is an industrial zone. So assume king and queen are parallel. So those two streets you could put little lines on, they're parallel. And we want to find the area of the industrial zone. Okay, so we have, I guess that this is 3 kilometers, but that's not enough to get an area, right? Area, you need base times height. We have a base, we don't have a height. But what we do have is another triangle over here with that information. You could get the area of this triangle. You have a base, you have a height. Here they've drawn it a little bit more clearly. So if these triangles are similar, then you can use the information from this triangle to figure something out about this one. So let's see how we might do that. First, we got to prove that these are similar, and so they've drawn the little lines in there. All right, so one of the ways that you can do this is, well, how would you do this, right? You can't use side, side, side because you don't have all 3 sides. And you can't use side, angle, side because you have one side for this triangle, but you don't have any of the either 2, right? So you need to have, to use side, angle, side, you need 2 sides to compare to each other on both triangles, but you only have one here. So that means you got to do angle, angle. And that's easy enough because if you look at angle GRK and angle NRQ, they form an X. So by opposite angles, you could say that those 2 angles are the same. And then you can kind of do this in other ways here, right? You've got G, K, N, and Q forming a Z pattern. So that means that angle GKR is the same as RNQ, right? That forms a Z pattern. So you've proven 2 angles are the same, so that's enough. Therefore, they're similar. Okay? So now that you've proven that these 2 are similar, there's a few ways that you could do this. So what they've done is they've just figured out the scale factor here. So the scale factor is 3, right? Because you do have this side and that side. Kg is corresponding to Qn. You do have to flip the triangle over. So imagine turning this again like a book. So you turn it from left, flip it over to the right, and the 2 triangles will line up with each other. So this and that go together, and we can get the scale factor. So 3 divided by 1 gives you a scale factor of 3. So if you blow this up by 3, you get that. All right, so we have the scale factor. How can we use it? Well, the area of this triangle will be the area of the small triangle multiplied by the scale factor squared. And you can get the area of the small triangle very easily because you have a base and a height. So let's do that. Area of the small triangle is half of base times height. So half of the base times the height. Base is 1, height is 1.4. So that's going to give you 0.7 as the area of your small triangle. So to get the area of the large triangle, we do scale factor squared, so 3 squared times 0.7, and we get 6.3. We want to remember our units. It is a word problem, so it does tell you that these sides are in kilometers, so we want to put that in our units. So the industrial area, the area of the industrial zone, therefore, is 6.3 kilometers squared. It is a word problem. Make sure you include a statement. Okay, so it's a bit of a long one, but the main takeaways here, make sure you can show that triangles are similar using either AA, SSS, or SAS, right? Angle, angle, side, 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 or side, angle, side. Make sure that if you know two triangles are similar, you can use information in one triangle to figure out information in the other, specifically side lengths, using the scale factor. And make sure that you can also apply the same technique to area. So if you have the area of one triangle and it's similar to another one, you multiply the area of one triangle by the scale factor squared. Okay, that's it for now. Have a good one.